Let's talk about graphing hyperbolas. So on this picture, I have an example of a hyperbola, and the curve for the hyperbola, or rather curves for the hyperbola, is in blue. The red, so here and here, the red dashed lines make what we call asymptotes for each of our curves. So the example for this hyperbola, let me get the equation up here. Whoops. For this hyperbola would be x squared over a squared minus y squared over b squared equals 1. And if you've been graphing ellipses, you'll notice that the equation is really similar to that of an ellipse. It's got x squared and y squared, a squared and b squared, and it's equal to 1. It just is subtracted instead of being added together. I want you to notice in this one, a and b are really close to each other. So a is negative 2.8 and b is negative 2.7. And the x squared is first and the y squared is negative. So if I were to show you what would happen if we switched from x squared being positive to y squared being positive, let me see if I can make these go away. These go away and this go away, and let's change. Now for this problem, we've got y squared is coming first and it's positive, and x squared is coming second and it's negative, but everything else is still the same. We still have the same a and the same b. If I turn back on the asymptotes, whoops, sorry. If I turn back on the asymptotes, that green set of curves also get sucked towards those asymptotes. So the asymptotes are the same as they were for the first one. It's just that this graph with the y coming first is hugging the y-axis instead of the other one that was hugging the x-axis. Let me turn it on. There we go. So the one in green, the set of curves in green, is the y squared is first, and the set of curves in blue is x squared coming first. So let me show you how you're going to come up with this set of graphs for hyperbolas. So let's go to the next part. Standard form. Just like all of our other conic sections, ellipses, and parabolas, hyperbolas have a standard form. If the x squared is first, then this set of graphs will hug the x-axis. And let's say the center is at HK. So let's say this is HK. If the center is at HK, then here's what we have. We have, let's see, my parabola will go this way, this way. They'll be opening in the direction of the x-axis. And here's what the A and the B mean, how we get those great asymptotes. So I'm going to undo the curves that I just did and go A squared. So I'm going to travel just much like an ellipse, A units to the left and A units to the right. And if I were drawing an ellipse, those would be the end points of my ellipse. And I would travel, change this to green, in the y direction, the B squared, I'd travel B units up and B units down. So if we were drawing an ellipse, we'd be doing exactly the same thing and we'd be finished. We'd be done. We'd just draw our ellipse in as best we could. But since this is a parabola, here is what we're going to do instead. Instead of drawing in an ellipse, I'm going to draw dashed box that has the top, the bottom, and the left and the right from the A's and the B's as the edges of that box. And I'll make this just like the previous graph. Through that box, I'm going to draw my dashed asymptote The asymptote goes through the center, and it goes through the bottom left corner and the top right corner of the box. And I'm going to do the same thing through the other two corners. Make them go through the asymptote, through the edges of the box and through the center as well. And then here's how I'm going to draw my hyperbola. Since the x squared comes first, that tells me that this opens to the left and the right, just like the x-axis goes left and right. So starting at the edge of my box on the far left, I'm going to draw one side of my hyperbola going sucked down towards that asymptote, and the other side of the hyperbola doing the same thing on the top. And to the other side of the, right on the edge of the box, one side going up to the asymptote and the other side, oh, that isn't pretty. The other side, that's better, going down to the asymptote. Okay, so the center is at HK. These two black dots right here are our vertices. I'll call this vertex 1 and that vertex 2. And notice those are A units from the center. So this would be H minus A, comma K, and this vertex would be H plus A, comma K. Okay, if you've graphed ellipses also, you will remember that we had focus points, or foci. And to find the equation of the focus points, we're again going to use c squared, where c is the distance from the center to each focus point. Now, this is going to be given by a squared plus b squared. So if you've recently worked on your equations for the foci for ellipses, it's a squared minus b squared, or b squared minus a squared, whichever one's bigger. This one is nice because it's always positive, a squared plus b squared. And the focus points, I need to give myself a little bit of room here, so I'm going to erase this and erase this, and I'm going to rename those vertices V1 and V2. And I'm going to write in the focus points. Focus point might be here, focus 1, and here, focus 2. And those are going to be C units away from the center. That formula still holds, whether it opens left, right, or like this one, opens up and down. And everything will be really, really similar. So I'm still going to have the center at HK. The number underneath the x value, the A, is going to be how far to go left and right. So again, A units to the left and A units to the right. That'll give me the edge of my box. The square root of the number under the y tells me how far to go up and down. So once again, I'm going to go up b units and down b units. That will give me the top and bottom of my box. And from there, I'll draw in my box. Okay. Lastly, I'm going to draw in the asymptotes. And this graph at first is going to look a heck of a lot like the one above. Now, if you notice, the only difference between the two standard forms is in the top one, the x is positive, it's not negative, it comes first. And in this one, the y is positive, and the negative comes after that. So the second form, for when y comes first and is positive, this graph will start on the top edge of that box and open up side to side, and the bottom edge of that box and open down side to side. Vertices for this are given, that would be here and here now. So this would be start at your center, and we moved B units up and B units down. So this vertex, let's say, would be H and then K minus B. And this vertex up here would be, I'll call it V2, H and then K plus B. And the foci, I'll call this focus 1 and this focus 2, are just inside each curve, tucked inside each curve. And we would use the same formula for both opening left and right and for opening up and down to find out C. Okay, let's do a couple examples. So let's work on example 1 right now. Example 1, we're going to sketch the graph of x squared over 25 minus y squared over 16 equals 1. A couple of things I want you to notice about this. For starters, it's equal to 1, so it's already nice in the standard form. Secondly, the x is squared and the y is squared, but they're being subtracted, not added, so I can tell right away it's a hyperbola. Last thing I want you to notice is we don't have those parentheses for the h and the k, which means just that the center for this is at 0, 0. Okay, so there's our center. All right, the number under x squared, our a squared is 25, which means if a squared is 25, a is 5. So we're going to travel left and right 5 units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The number under the y squared, I'll do in green, is 16. So b must be 4. So that means we're going to travel up 4 and down 4. And from there, we can draw the outline of our box. Once we have that drawn, then we can draw in our asymptotes. So go through the center and 2 diagonal corners, and same on the other side. Okay, now all of this would have been exactly the same whether it started with x squared or with y squared. It's just now we need to figure out whether our graph opens up or down, up and down, or left and right. And since the x squared comes first, this opens left and right. So I'll go to the leftmost side of the box right there at -5. I'll draw one curve down, gets sucked towards that asymptote, and its mirror reflection on the top. And I'll do the same thing at +5, one curve, and then the mirror reflection on the bottom. And those points, each one is a vertex. So the first vertex is at -5, 0. That's this black dot. And the second vertex is at +5, 0. Okay. Almost lastly, we're going to find the focus, or the foci, focal points. So we're going to use c squared equals a squared plus b squared, which is going to be 25 plus 16, which is 41. Okay, so that's some decimal. Let's quickly calculate what that decimal is. So the square root of 41 is 6.4 approximately. So we're going to travel 6.4 units away from the center. So 6.4 units, or the square root of 41 would be here. That's one focus point. And we're going to travel from the center backwards, -6.4, or negative square root 41, and that'll give us our other focal point. So if we wanted to write this, our focal points are at x equals plus or minus the square root of 41 and y equals 0. Now sometimes you're asked to find the equation of the asymptotes. If you're asked to find the equation of the asymptotes, what you want to remember is that these lines right here, your asymptotes, Well, for this example, they go through 0, 0. So the y-intercept is 0, which is lovely. And if we're looking at rise over run, notice the rise over run is really just the corners of that box. So it's going up 4 units and over 5 units. So our slope for this asymptote is positive 4 over 5. Since the y-intercept is 0, the equation of that line is 4/5 x plus 0. Moreover, the other asymptote is symmetric. It has the same slope, it has the same y-intercept, it's just going down. So this one would be negative 4/5 x plus 0, because again, the y-intercept is 0. So in some problems, you do need to find the equations of the asymptotes. I'll point that out in the next problem too. Okay, let's go on to example 2. Example 2 is okay, except it's not equal to 1. It's equal to 36. So I have y minus 3 all squared minus 9 times x plus 1 quantity squared equals 36. I need it equal to 1. So just like when we were doing the ellipses, I'm going to divide everything we have by 36. So now we have y minus 3 all squared over 36. 9 and 36 reduced to a 4 in the bottom, so x plus 1 all squared over 4. And 36 over 36 is 1. Great. So the center for this hyperbola is at negative 1, 3 from the h and the k and the x plus 1 and the y minus 3. So let's go to negative 1 for x and 3 for y. There's our center. Okay, it looks like from this standard form here, the number underneath the x value is 4. So that means that a is 2. So we're going to go left and right 2 units. 1, 2. That puts us at 1. And backwards puts us at negative 3. And those are the left and right edges of our box. Remember, I'm starting at the center and going to the right 2 and then back 2. And for the y values, if b squared is 36, that means that b must be 6. So we're going to go up 1, 2, 3, 4, 5, 6. And down 1, 2, 3, 4, 5, 6. And those are going to give us the top and bottom of our box. So let's draw that in. Okay, I'm sensing I'm going to need more room. So I am going to get out my eraser and erase the top so I have some room to work. Okay, next thing we need to do is draw in our asymptotes. That x and y axes is not going to erase, but we can live with that. Okay, so if I draw in my asymptotes through the center and one diagonal through the center and the other diagonal, let me erase that really quickly. There we go, make it a little more dashed. All right, and we can get a pretty darn good picture of what our ellipse looks, our hyperbola looks like. So remember, since this one has the y coming first, it opens up and down. So we're going to start at the very top edge of the box and the very bottom edge of the box, and those are our vertices. So starting at the very top, we're going to go out and out to meet the asymptotes. Let's try that again. Better. Out and out to meet those asymptotes. So it looks like those points, let's see, we started at 3 and we went up 6. So this vertex must be at x is negative 1 and y is 9. Starting at 3 and moving up 6. And this vertex must be, again, at x is negative 1, but we went down 6. So When we start at 3 and go down 6, we end up at negative 3. Okay, and the foci, for the foci, c squared equals a squared plus b squared, so 36 plus 4. So the square root of 40, which is 2 root 10. Okay, so you can do like we did in the last problem. You can get out your calculator and go up and down 2 root 10 or the square root of 40. That's just a little bit less than the last one, which was 6.4. So it's a little bit less than 6.4. So we'll go up and down 2 root 10, which is just above 6. So up and down 2 root 10 from our center. So this is 2 root 10 units. Whoa. And then down 2 root 10 units. So those yellow dots are our focal points. This focus is x equals negative 1 still, and we're just moving down from the center, so 3 minus 2 root 10. And this focus up here stays at x equals negative 1, but starting at the center value of 3, it's going to move up 2 root 10. Okay, let's do one more example. Let's do this example. 4x squared plus 16x plus 9y squared minus 20. Like I said in the last problem, if you've been working on ellipses, this is going to be really similar to the ellipses. 4x squared, although I think there is a mistake here. This is an ellipse. Let me change my example. I want to make this minus. There we go. It was an ellipse. Now it's a hyperbola. Okay, 4x squared plus 16x minus 9y squared. That's a hyperbola, and minus 20 equals 0. So here's what we're going to do. Just like when we were graphing ellipses, we're going to complete the square on the x's. Now the y's has a y squared but no y value, so we don't have to complete the square on the y's. So here's what we're going to do for the x's. Factor out the leading coefficient. So factor out the 4, but only do it from the x squared term and the x term. Okay, 9y squared, and then we're going to scooch the 20 to the other side. Now inside those parentheses, we're going to complete the square. So 4 divided by 4 is 2, and 2 squared is 4. So 4 is the number that I need to add to both sides. Okay, so the 4 inside these parentheses, we need to balance the equation by adding it to the other side. The problem is that this number wasn't really a 4 that we added in here. It was a 4 that was also being multiplied by that black 4. So when we add it to the other side, we need to multiply also by whatever number was in front of those parentheses. So this turns into 4. Let's see, factoring x squared plus 4x plus 4 is x plus 2, all squared. Minus 9y squared equals, let's see, that's 16 plus 20 is 36. Okay. Just like in the previous problem, it's not equal to 1. So I need to divide everything we have by 36 so that it gets in that standard form. So now we've got x plus 2 all squared over 9. The 36 and the 4 we're going to reduce to a 9 in the denominator. The 9 and the 36 by the y we're going to reduce to a 4 in the denominator. And now our 36 over 36 is 1. Great. So we have center is at negative 2, 0. Okay, let me draw my graph here. Let's try that again. And yes. Oh, this is funny. Okay. Oh, yeah, no. Sure. There we go. That took a minute. All right. So center is at x equals -2. Y is 0. Here's our center. The number under the x is 9. So that means if this is a squared, then a is 3. So we're going to go left and right 3. 1, 2, 3. 1, 2, 3. That'll give us the left and right edges of our box. The number under the y value is 4. So that means the square root of that is 2. So we're going to go up and down 2. 1, 2. And down 2, 1, 2. And it gives us the edges of our box, through which we can draw our diagonal lines, giving us our asymptotes. Okay, almost done. So our x's are coming first, and they're positive. So this one opens left and right. So let's start at the leftmost edge and the rightmost edge, and that'll give us our 2 vertices. So I'll call it V1 and V2. And draw one side at the top, one side at the bottom. There's a pretty decent picture of our hyperbola. And it looks like those vertices are at the points -5, 0 for V1, and V2 is at 1, 0. Okay, and then finally we have our focal points. C squared equals A squared plus B squared, so 9 plus 4, which is 13. So C is the square root of 13. So that's just a little bit less than 4 units. It's 3 point something. So we're going to go 3 point something, root 13 to the right. So here is whatever this distance is, square root of 13, and root 13 from the center to the left. So our focal points are at x equals root 13, y is 0, and x equals negative root 13, y is 0. Or you could just write plus or minus root 13, comma 0. I've been a little neglectful about finding the equations of the asymptotes. So if you're asked to find the equations of the asymptotes, remember the green lines that I've drawn in here are your asymptotes, and those have rise over run, those have slope. They went up 4 units. I'm sorry, up 2 units. So rise of 2. And they went over 3 units. So the top one has a slope of positive 2/3. The bottom one is going to have a slope of negative 2/3. The top one, let's see, it goes through the ordered pair -2, 0. So you could, that's our center, it goes through this point. So you could do y minus 0 equals 2/3 x plus 2. Or in other words, y equals 2/3 x plus 4/3. You could do a similar thing for the bottom equation. Y minus 0 equals negative 2/3 x plus 2. And distribute, so you get y equals, I'll go over here, negative 2/3 x minus 4/3.